on, everybody? It is your boy Pete, and today we're going to be looking at Newton's second law of motion. So if you haven't already, go check out Newton's first law of motion. There will be a link on the screen right now to go check out Wallace's vid. You got to learn that before you learn this stuff. Alright, so in Wallace's vid, there was no net force acting on the object. But in Newton's second law of motion, we do have a net force on the object. So imagine you're pushing a cart on a frictionless surface and there's no wind resistance. All right. Now imagine if you were to push that with twice the force. Okay. The acceleration of the cart would be twice as much. So Newton postulated to himself, how are these two quantities related? How is force and acceleration related? And he decided that they were directly proportional. If you doubled the amount of force you put in, you would double the amount of acceleration. But then he realized there must be another factor. Because, for example, if you push an elephant, the elephant definitely won't accelerate as much as the cart did. So now imagine if we had two carts that were both pushed. If we still use the same amount of force, the acceleration wouldn't be the same. It'd be half the acceleration it was with only one cart. So then Newton realized that mass and acceleration are inversely proportional. If you double the mass, you halve the acceleration. If you increase the mass, you lower the acceleration. So the acceleration equals sigma f over m, where m is your mass, and sigma f is the vector sum of all the forces from the environment acting on it, all the external forces, the ones we talked about before, like friction and wind resistance. So if you multiply through by m, or the mass, you get that mass times acceleration equals sigma f. Now, we commonly see it the other way. The sum of the net force equals your mass times your acceleration. And if we look at the units quickly, mass, the SI unit for mass is kilograms, and the SI unit for acceleration is meters per second squared. So 1 Newton of force, the SI unit of force, is a kilogram times a meter over second squared. So when we do problems involving Newton's second law of motion, we like to draw free body diagrams. And free body diagrams help us see where the net force is on a certain object. And we usually deal with free body diagrams that are not as involved as the one you see here. But the idea here is that we can calculate the net force more easily and see it more easily with a diagram. So now we're going to talk about the vector nature of Newton's second law of motion. So if we're dealing with two-dimensional motion in kinematics, we want to express each component in a different term. So we have our x component of force as our mass times acceleration in the x direction, and then we have our y component of force, which equals our mass times our acceleration in the y direction. So yeah, that's about it for Newton's second law of motion. There's a short look at Newton's second law. Get excited for Newton's third law, which will be here shortly. And as always, guys, the more you know, the better you are. Peace.